This is one simply supported beam with uniformly distributed load. So our first task is to determine the support reactions. So let me draw it here once again. The support reactions at A is RA and support reaction at B is RB. And the beam is subjected to a uniformly distributed load with intensity small w. So this is so total load on the beam is what? If length is L, then the total load is W into L. And the resultant force will act through the midpoint of the beam. This is WL, which is acting through L by 2. That is the midpoint of the beam. Now if we apply the equation of statics, that is what we will get. If we apply f of y is 0, then Ra plus Rb is equal to Wl. Now let us apply moment about A is 0. This is point A. So Rb into L minus Wl into L by 2 is 0. That is Rb is Wl by 2. As Rb is Wl by 2 and Ra plus Rb is Wl, so Ra is also Wl by 2. Because this is a symmetrical, loading is symmetrical, so both Rb and Ra are same and they are Wl by 2. Now how to draw the shear force and bending moment diagram? What we will do? We'll take a section, say here, at distance, any distance x, we'll take a section and we'll draw the free body diagram. That is, if we draw the free body diagram, so this is point A and we know that here the reaction force is WL by 2. Now the distributed loading, if this length is x, then total load on this section is W into x, and that will act through x by 2. This distance is x by 2. Now unknown forces, internally resistive forces, that is shear force at this face, at right hand face, this is the direction of Vx and this is the direction of Mx. So these two we have to calculate. So first let us calculate what is Vx. We shall apply f of y is 0. If we apply f of y is 0, then WL by 2 minus Wx minus Vx is 0. Where we have to mention another point, that is the limit of x is greater than 0, less than L. This is the limit of x here. That is Vx. If we take Vx at this side, then we will get WL by 2 minus Wx. So this is the expression for shear force. Now, if we want to calculate Mx, then what we will take? That is summation of M. If this point is C, that is moment about C is 0. If moment about C is 0, then what we will get? That is Mx plus this force is W into x, and distance of Wx from C is x by 2 minus this is WL by 2 and distance is x is 0. That is mx becomes what? wl by 2 x minus wx square by wx square by 2. So this is the expression for bending moment at any distance x. So now if we want to plot the shear force and bending moment of the beam, then how it will look? Let us take this here. So first let us plot the shear force. Say this is x, and here this is shear force. Now at x equal, now let us come to this equation. When x equal to 0, then Vx is WL by 2. Then Vx is WL by 2. Let me, this is, say this is WL by 2. And it's linearly varies with x, and we can see if x equal to L by 2, then Vx becomes 0. At x equal to L by 2, say this is the line for x equal to L by 2. This is x equal to L by 2 line. So Vx becomes 0 at x equal to L by 2. X equal to L by 2. Let me draw it with red color. L by 2. Next, at x equal to L, it becomes minus WL by 2. So the diagram will be like this. So here this is minus WL by 2. Minus WL by 2. So this is the shear force diagram. Now let us draw the bending moment diagram. How the bending moment will vary. This is x and this is bending moment. So now let us come to this expression, that is, this is the expression for bending moment. At x equal to 0, bending moment is 0. And at x equal to L by 2, at x equal to L by 2, what will be the value? At x equal to L by 2. What is the value of bending moment? Mx at L by 2. That is, this is WL square by 4 minus here WL square by 8. That is WL square by 8. So this becomes WL square by 8, and here you can see the order of x is square, and this is the equation of parabola. So this is the equation of parabola, whereas this is the equation of straight line. The Vx was straight line. This red line denotes the shear force diagram, that was straight line, but Mx here is a parabola. And how it will vary? That is like this. And here its value is WL square by 8. So this is the value at x equal to L by 2. And x equal to L, further at x equal to L, we can see that Mx becomes 0. So this is the bending moment diagram. So we have completed our task. We have drawn both the shear force and bending moment diagram. I am doing here, that is, the beam was like this, simply supported beam with uniformly distributed loads. This was the beam and loading was W, length was L, and the shear force and bending moment diagram was shear force so here minus WL by 2 and it was plus WL by 2. And bending moment, what about the bending moment? Sorry, what about the bending moment? Bending moment was heading like this. So here the value was WL square by 8. And we can see this is the maximum value of bending moment. So this is nothing but a max. And we have observed one thing, where bending moment is maximum. At this point, shear force Vx is 0. So this is the observation from this bending moment diagram. Later we shall develop these equations, but we can note here that where bending moment is maximum, there shear force is 0. So this was the bending moment diagram about that beam. Now